Okay, hello everybody. I hope all of you are safe and sound and everything is going well with you. I'm going to start our next session. As you know, we have talked about variational approach and we derived Euler-Lagrange equation to find an extremum function of a functional problem. Euler-Lagrange equation can be written as follows. As you can see, derivative with respect to x of partial derivative of f with respect to y dash minus partial derivative of f with respect to y is equal to 0. If we solve this equation using boundary conditions, we can find the solution to the functional problem, and functional problem is the problem which is going to find an extremum solution for this integration, where f is function of x, y, and y dash, and y is a function of x, and y dash is the derivative of y with respect to x. To find an extremum function y which is going to minimize or maximize this integration, we must solve Euler-Lagrange equations with appropriate boundary conditions, as we discussed in our previous chapter. In this our previous session, in this session, I'm going to solve an example to make you more familiar with this approach to find an extremum function for functional problem. Let's speak about our first example in this course. We talked about a brachistochrone problem in our first session. In this problem, we wanted to find a path from point 1 to point 2 in order to have the minimum amount of time to travel from point 1 to point 2 in a smooth path, and we show that the amount of time can be calculated using this formula. If for the special case I set initial velocity 0, or in other words, I release the object from the rest, I can say v1 is equals to 0, and I can set the origin in any arbitrary point. I set the origin at the first point, so I can say x1 and y1 is equals to 0. If I do so, I will simplify the equation A to equation B. In this equation, as you can see here, I is equals to 1 over square roots of 2 multiplied by g, all of them multiplied by integration from point 1 to point 2 of square roots of 1 plus y dash by 2's, all of them over y d of x. Let's speak about this problem. As you can see, the coefficient of this integral, as I can show you, this coefficient is a constant number and does not affect the amount of extremum or minimum. So I can say that the function f in Euler-Lagrange equation can be written by this equation, or in other words, I can say f is uh, 1 plus y dash by 2, so all of them over y, and all of them power to 1/2. So I can use Euler-Lagrange equation directly and to find the differential equations governing to y. In your book, the final differential equation are given directly, but I'm going to explain more to in the procedure to finding this equation. So let me open some handwritten notes, and I'll come back soon. Okay, as you can see here, our functional can be written as follows, and function f can be written by this formula. As you can see, f is equals to square roots of 1 plus y dash by 2 over y. I can rewrite this equation as 1 plus y dash by 2, all of them power to uh, 0.5, and all of them multiplied by y power by minus 0.5. Okay, I can calculate partial derivative of f with respect to y simply by this equation. As you can see, the first term is not function of y, but this term, the second term, is a function of y. The derivative of this term with respect to y can be calculated as minus 0.5 multiplied by y power to minus 1.5, as you can see here. And I can calculate partial derivative of f with respect to y dash in the similar way. You can see the formulation here. It's very simple. You can do it by yourself. And if I want to calculate the derivative of this term with respect to x, as you can see, y and y dash, all of them are function of x, so the derivative of this term with respect to x can be calculated by the chain of rules, the derivative chain of rules. I'm sorry, the rule of chain of derivatives, and I can say that this derivative can be calculated by this formula, partial derivative of this term with respect to y multiplied by y dash, and partial derivative of this term with respect to y dash multiplied by y double dash. If I do so and replace partial derivative of f with respect to y dash from this part, I can find the amount of partial derivative of I'm sorry, I can find the amount of derivative with respect to x of partial derivative of f with respect to y dash. This is our last formula for the second term of the Euler-Lagrange equation, and if I substitute this term and this term in the Euler-Lagrange formula and do some simplifications, as you can see in our next, let me As you can see here, if I replace these equations, these terms in the Euler-Lagrange equations and do some simplifications, I can show that you can follow this formulation by yourself. I can show that y double dash is equals to minus 1 plus y dash over by 2's, all of them over 2 multiplied by y. This is the formulation we have found here in our problem, and to solve this problem we need to do some simplifications. In this equation, as you can see, we don't have independent parameter directly in our formulation, so we can do some change of parameters. We can say that let's assume that y dash is a function of y. We name y dash as u, so we can say that y double dash is equals to derivative of u with respect to x. We can multiply and divide this equation by dy and replace the position of dy and dx with each other. So we can say that y double dash is equals to du differentiation of u with respect to y multiplied by d of y over d of x. This term is what we have defined before. This term is u, so we can say that y double dash is equals to u multiplied by derivative of u with respect to y. And if we use this simplification and substitute it in our formulation, we can see that integration, we can and do some integration. We can show that integration with respect to u of u d of u over 1 plus u dou is equals to integration with respect to y of 1 over 2y with respect to d of y. If we do integrations, we can show that natural logarithm of this term 1 plus u by 2's, all of them over 2, is equals to minus logarithm of y over 2's plus a constant number, name it c. If I powered this equation, I can easily show that 1 plus u by 2 is equals to u power by minus 1 multiplied, this is multiplication, multiplied by e multiplied by c. I name this parameter c1. I can say that 1 plus u by 2's, all of them multiplied by y is equals to c1. This is the formulation which have been represented in here in example 2.1 in your book. Okay, and from now on we can do some integrations to find the value of y of x. We replaced u by y dash and so on. If we do some integrations, we can find x as a function of y by these equations. Okay, doing this integration maybe somehow hard. We don't intend to necessarily solve these types of equation integrations. I just wanted to know the procedure of finding a functional and how to solve this kind of problems. For example, for these equations, by doing some change of variables, I can substitute y by this problem and show that x and y can be calculated by these formulas, and this formulas is easily a cycloid formula, which shows a curve generated by the motion of a point fixed to the rolling wheel, which is rolled along the x-axis. This is one solution we can find for the brachistochrone problem for a special case, as we mentioned before. Okay, this is enough for this video. You can find the continue of our session in our next video.